He's the only one who's good at it. I think because
I did get emailed a couple of questions about that train question in 4.1, so let's take a look at that.
It took me a couple tries, but
I need to do it today.
I eventually got it right.
So I have math homework to do, and then another math homework to do. I have 2 days of math homework to do.
So we're looking at expansion joints here. Things expand when they get hot. So train tracks, for example, are built with expansion joints so that when they get hot, they can expand without buckling. Other things are built like that too. Flooring in houses, for example, if you put in laminate flooring, you'll need to leave a 1/4 inch space around the edge so that when your floor expands and contracts, there'll be space to do that. Or have you ever driven by a house that had vinyl siding that was all buckled? That happens when you don't put expansion area in there. So vinyl siding needs to be tacked on with a little space to move yet. You can't hammer those nails in hard. In fact, a friend of ours was using a nail gun to put their siding on, and we're like, no, don't do that. That's going to be too tight. It's going to buckle when it expands. So here we see some train trouble. Train tracks are made of metal. Consequently, they expand when it's warm and shrink when it's cold. When riding in a train, you hear the clickety-clack of the wheels going over small gaps left in the tracks to allow for this expansion. Suppose you were a beginner at laying railroad tracks and forgot to put in the gaps. Instead, you made a track 1 mile long that was firmly fixed at each end. On a hot day, suppose the track expanded by 2 feet and therefore buckled up in the middle, creating a triangle. So we have all the buckling going on in one space here. You probably have more or less buckling. This one has 2 feet of buckling, but you have different amounts probably depending on your particular version of the problem. So you have a 1 mile long track that's expanded by 2 feet. So there's 1 foot added on each side. So whatever your expansion is, put half on each side. So mine is expanded by 2 feet. So I put 1 foot extra on each side. So that makes a triangle in the middle. Well, in the word problem it does. I don't believe it would actually all occur at one point, but it's an interesting problem nonetheless. So here's our unknown height that we're trying to find. Happily, we have a right triangle, so whenever you know 2 sides of a right triangle, then you're all set. The original track was 1 mile long. Who knows how many feet are in a mile? Good. 5280. 5,280 feet. So now we have half of that over on this triangle. So let's divide that in half. We get 2,640 feet. Okay, so all of us will have an X on one side and 2,640 feet. But the slanted side is going to be different. Mine expanded by 1 foot, so I have this 2,640 feet plus 1, half of the 2. So all of us will have different numbers there. But you put half of the expansion there on that hypotenuse. So let's go ahead and find x now. Okay, so as you're using the Pythagorean theorem, the sides making the right angle are the a and the b. So the x and the 2,640 are a and b. The hypotenuse is the longest side there, in this case 2,641 feet. So we'll go ahead and do the squaring. 2,640 squared is 6,969,600. And then I'm squaring 2,641. That's 6,974,881. Next, we'll go ahead and subtract from both sides of the equation to get the x squared by itself. So we're going to subtract the 6,969,600 feet from both sides. That leaves 5,281. And the last step is to take the square root of both sides. Now you'll have to be careful to round to one decimal place. One of the answers that was emailed to me was correct, except the student had rounded to 2 decimal places because we were doing that in class. But the problem does call for rounding to 1 decimal place. So here I would say that the second decimal place is 5 or above, so I make the 6 into a 7. And that's just saying I'm closer to 72.6 than I am, I'm closer to 72.7 than I am to 72.6. Just 3/100ths away from 72.7. Anybody have any questions on that problem or another problem? Okay. Then let's continue on looking at proving the Pythagorean theorem. Does anybody need a scissors to cut out templates? Can you come and get one from me if you need it, please? Okay, they're up here. Yes?
I'm pretty sure someone over there had a question.
Oh, okay. What was it?
I was just going to ask about the sets and the subsets one about the sun and the moon and the earth. That one I was confused.
The sun, moon, and earth?
Yeah.
So we talked about that a little bit in class. Let's look at it again.
I'll do that one tonight. And I'm rather not supposed to. That's 2020. Huh? 2021 first steps. Wow.
So we're looking at subsets of sun, moon, and earth. These are power sets. So we covered this in more detail on Monday's class, March 2nd, if you're looking back at videos later on Sunday trying to figure out what's going on. So we're looking at all the possible subsets of sun, moon, and earth. And we had the empty set. We have all the sets with just one element, and I'll abbreviate those with just one letter. Then we have all the sets with 2 elements. Which one did I get? Thank you. And then we could have the actual complete entire set. So the power set is all the set of all the subsets you can make, and in this case there's 8. So 8 different subsets that you can make. All the different ways you can take the sun, moon, and earth and make sets out of those. Okay. Any other questions? Actually, I think I'll leave this under here. It writes a little better that way. Well, we were looking at proofs of the Pythagorean theorem, and those proofs had depended on geometry, because geometry has been around for millennia, algebra not as long. So the Pythagorean theorem would have been proven originally using geometry. So we had looked at a square that was a plus b and another square that was a plus b, and we used that to prove that the Pythagorean theorem was true. Okay, so each of these squares is a plus b wide and a plus b tall, or a plus b squared for the area. Well, today we're going to look at another arrangement we're going to make a square c squared. Anybody else need scissors? Okay, so take your templates and make a square c by c. So the outside is going to be c. So I would like the c's to be on the outside. All your templates should have the c's on the hypotenuse, and an a on the long leg, and a b on the short leg. Okay, the legs are the sides making the right angle. Remember, this would work for any right triangles that were all the same. So I could have used my other cutout templates. Let's get that all in there, okay? So we have a square c by c. So the area of the square is c squared. Now there's a square that's in the middle that I haven't filled in yet. The length of that square on a side would be the length A minus the length B, because you have the long side here minus the short side there. So there's a square A minus B. Also, does anyone remember how we know that these two angles make a right angle? How do we know these two angles together here make a 90-degree angle? How do we know they're not just 88 degrees or 93 degrees? Anyone remember how you know that? This only works if you have a square, so we need this to be a 90-degree angle. Does anybody know how we know this is 90 degrees? Okay, how many degrees make up all the angles in one triangle? Yeah, 180. Good remembering. Okay, so 180 is in the whole triangle, and now I've taken away the corner, which is 90 degrees. So once I take away the corner, the two smaller angles, the two acute angles, those are called, add up to 90 degrees, because there's 180 in the whole thing, and I took away 90. Well, all these triangles match. So this angle up at the top of the green is the same as this at the bottom red. So these two angles add up to 90 degrees because they're the same as these two angles in any of the right triangles. So we do have a square, and the dimension of the square is c squared. So this is proof 2, and we're going to have to draw this figure onto the paper. So let's go ahead and work on that. So you'll need to start with a square. If you're not using a ruler or graph paper, then please take another piece of paper to work with the lined paper you have and make your own homemade ruler. Okay, so if you only have lined paper instead of graph paper to make a square, you need both sides the same. So go ahead and count off some units here. I'm going to make my square 7 units by 7 units, but you could make it however you wanted, just so it is in fact square. There will be a little bit of graph paper with the problem on the quiz so that you can draw nice straight lines, and as long as you have a straight edge with you. So we're just drawing this picture because you can't very well hand in your templates on a quiz. So I need you to transfer the image that we have created onto the paper. Now you need another piece of paper to make your corner. So you can use your piece of paper that you just pull out of your notebook here to make a triangle. Then you'll get a nice sharp corner. I'm going to use a pink one because that way it'll show up better. Where did I put it? How can I be sitting right here, haven't moved 2 feet, and I can't find something I had at the beginning of class? Okay, well, happily I have other paper that's colored. In fact, you could use your placard if you want. If you have no other loose paper, your placard has a corner that's perfectly square. All right, so I'm going to let this piece of paper look like my red triangle here. I'm going to mark off where I'm crossing the corners because I'm going to do this again all around the whole square. So use the corner of your square piece of paper, and if you mark off where you cross the corners, you can do pretty nicely similar drawing, and it'll look pretty good. I used to use a ruler to do this, but you know, rulers have rounded corners, which makes sense, but it makes it a little trickier to draw here. Okay, so it doesn't come out perfect, but that's pretty good. And we rely on our A, B, and C labeling to indicate to the reader that these are supposed to be all the same right triangles. So make sure you put your labels on. So C on the hypotenuse, A on the long leg, and B on the short leg. And then do put your corners on to show these are all right triangles. So once you've labeled these, even if your drawing's not perfect, the reader knows that you intended these all to be the same right triangle. Remember, this will work with any right triangles, not just the ones that you made templates for, but any right triangles that are all matching. Well, once you get that drawn, then we're going to do some algebra to complete the proof and to describe what the picture is showing. Of all of our proofs that we look at, this one has the least drawing and the most algebra. So if you're more of an algebra person, this might be the proof for you. Okay, everybody have their drawing ready to go? Just a little bit longer. I'll make this bigger in the meantime. All right, we have c squared. We have a square, c by c. Remember, we're looking at areas here, and the area of a square is its length times its width, or c times c in this case. Well, that space c squared is comprised of 4 right triangles. 4 right triangles plus 1 square. Oh, we did not label the square. Who remembers the dimensions of our square? How wide is it? We need that. That's important. Remember how we get the square? The length of the square is the long leg's length minus the short leg's length. So A minus B. You can see it in the picture a little bit there. A minus B. So label that on your drawing too, please, so that your reader knows what you're talking about. Namely me when I correct your quiz. But really, in real life, when you explain this to a friend, then they'll know what you're talking about. Okay? So we have these 4 right triangles and we have the square. So now we're going to describe the area of those. Remember the area of a triangle? 1/2 base times height, right? 1/2 base times height. So our triangles have a height A and a base B. So we have 4 times 1/2 times A times B. So each of the right triangles is 1/2 times A times B in its area. And then we're adding to that the square, and the area of the square is its base times its height. So this is a little square corner there, okay? So the base is A minus B, and the height is A minus B. So the area of the square is A minus B times A minus B. So now we do a little bit of algebra. We're not doing anything on the c squared, but the 4 times a half is just 2. So you have 2 times A times B. You don't have to keep putting the dots in for multiplication once you have the 4 times a half. In fact, if you like little x's for multiplication, you can use those instead. Now, who remembers how to do the multiplying here? We have A minus B times A minus B. Does anyone remember an algebra term that we use to help remember how to do this?
Distribution.
It's distribution, yep. And then the specific distribution, we had another name. Yes?
Foil?
FOIL, yep, that's the word. Distributing using FOIL. Thank you. Distributing using FOIL. So FOIL stands for first, outers, inners, last. And you don't have to write the FOIL in the first, outers, inners, last, unless it's helpful to you to know what you're doing. Okay. So we want to add on A minus B times A minus B. So I'm going to put the plus sign again. And then I'm going to do the first, outers, inners, last multiplying. So first means the first inside the parentheses here. So it's a times a for the first, or A squared. Outers is the outside values in the parentheses, so the A times the negative B. Who remembers the positive times the negative is what? Negative, yeah. Negative. So negative A times B. It doesn't matter if you write B times A or A times B, because 2 times 3 is the same as 3 times 2. Multiplication is commutative. All right, another inners then. Inners means the inside terms, so the negative B times the A. So again, a negative A times B, I'm going to say. And last means the last in each set of parentheses. So negative B times negative B. And what's a negative times a negative? Positive. Good. So positive B squared. So a lot of algebra there. But now we see what's going on. We have 2AB, and we're taking away an AB and another AB. So this is like 2 apples minus 1 apple minus 1 apple. No apples are left. No ABs are left. We only have C squared and then A squared plus B squared left. So this proof has the most algebra and the least amount of drawing. And if that's the one that clicks for you, then this is the one you should make sure you understand well, okay? So we start with a square that's C squared. We describe what it is. 4 right triangles in a square. We say what those areas are. And when we do the algebra, what we have left is the Pythagorean theorem. Okay, now I recommend drawing lines between your proofs because I get an awful lot of proofs handed in that have parts of their proofs all goofed up. It's like algebra from one proof going with pictures of another. Does anybody have questions on proof 2? Proof 3 has the least amount of algebra at all. And proof 3 starts with the C squared picture again, so we might as well just go ahead and draw that, all right? So proof 3 starts with the C squared picture. I think I'm going to work at the bottom of the page this time because then later I can do pictures at the top and you can still see them on the screen. So I'm going to put this picture again down below. Well, you know what? You can see the screen. I might as well put it out there. So same thing that we did before. We're just transferring the drawing of C squared. And I'm putting it at the bottom so that you can see the work and the picture at the same time. So I had made the last one 7 by 7, so that's what I'll do again. But it doesn't actually matter how big you make your square, just so that it is square. Well, I guess it needs to be big enough so you can write in it. If it's too tiny, you can't really see what's going on. So we'll get our square drawn. Then we'll use a corner from another piece of paper to simulate the triangles we have going on. We get a lot of practice drawing this one, so this one should come out pretty good, I hope.
Yes. I know, like this. It doesn't look me.
It kind of reminds me of a pinwheel.
Like do it. You should be able to do it with any size.
2, 3, 4, 5, 6.
So remember to label all of your A, B, and C's and your right angles. And that will show everybody that you are in fact drawing 4 triangles that are exactly supposed to be the same. Now this takes practice, and that's one of the things the tutors will practice with you each week. So once you've settled on one of the proofs that you like, the tutors can help you practice each week to make sure you have the drawing down to show what's going on. So this proof takes the least amount of algebra. We're just going to point out that this is c squared. Oh, I keep forgetting to label that middle box. Do not forget to label your middle box. So your middle square, a minus b, its length and width are both a minus b. Now notice how we used all of these 5 shapes, the square and the 4 triangles, to make c squared. What I'm going to ask you to do is to use those same 5 shapes now to create a squared plus b squared, because that's what we're headed for, right? Our last proof said, the Pythagorean theorem, that the c squared equals a squared plus b squared. This area that we made up with these 5 shapes can be formed exactly into 2 squares that are of dimensions a squared and b squared total. So I'm going to ask you to reshape these like a puzzle, to work on them until you can find 2 squares, a squared and b squared, at the same time using all 5 shapes, so that you've used all the area you used here to make 2 squares, a squared and b squared. That's the essential essence of the Pythagorean theorem, that this area equals the same area as 2 squares, one a by a and one b by b. So you work on that on your own, move the pieces around like a puzzle, and I'll come around and help you.
That's what. Bless you.
So you do it?
Okay. And then we need to make one that's like a by a.
This side is an A.
A by A. A by A. B by heavy. No. We're going with that. I'm excited. I get to get my package and get the hammer. So when you come over, we can do that. Well, where my friend is from, they can actually loft on, like,
Really?
yeah, and like the maintenance does it for them. They don't actually have to do it, but they only get 2 times to do it, so.
This is your class activity, so you need some templates. If you don't have templates, I have one extra set if I can figure out why I couldn't find them a minute
I
ago.
don't know either.
Professor adds it. Is it next to your computer? On the other side.
Oh, thank you, good eye.
My template isn't incomplete, it's just, well, yeah, it is incomplete. I already
You
have-
need a little more, you need a little more. Okay, so do you want to use mine instead?
Sure.
Okay, so use mine. So if you don't have a template, you can
Situation.
borrow your neighbors and trace it, and then cut it out, okay? So maybe
Part of it forms an L.
I was like, wait.
Like this.
You were right that you put the C parts together though.
you don't happen to have 3x5 cards, do you?
Fine.
If you have 3x5 cards, that's the easiest.
Me. No, where's my B? B. Where's B?
Yeah, you're doing very good. This is your author calls this a fat L shape.
Oh, it's not. I'm getting that. I'm done.
Working on an L shape.
I'll give up.
It's Friday. It's Friday.
You have this fat L shape.
Oh. Okay.
Yeah, but that's very creative. Fat L shape.
Running
So
for
that
those
says, yeah. So this square right here is B by B.
Okay. Oh, I see.
And this square right here is A by A.
Okay, I see
Wait,
it.
did they figure it
A,
out?
A, A, B, B, B.
Yay.
I'm done. Wait, this is our class activity?
Yes.
I need to take a picture before I forget. Where's my name tag? Missy, class activity. What did you do? Where'd you leave it wrong?
Okay, your author calls this the fat L shape, and I see some of you have it.
Where's my name tag?
Because I don't know where mine is.
So to make a fat L shape, you need 2 rectangles, right? So we make rectangles out of our triangles, but we have to use all the area we used to make c squared. If we use all the area we used to make c squared, then we're going to have, we'll be on our way to a proof. If you don't use all the area, then you can't say, well, this c squared is equivalent to whatever you're talking about if you haven't used all of the c squared. So this is the fat L shape your author is talking about, but I told you you had to make a squared plus b squared. Can anybody see 2 squares in this shape? Can you picture 2 squares here? Like, no, it's a bunch of triangles in one little square. Okay, here, what if I go like this? Does that help? Okay, now you have 2 squares. 2 squares, 1 big square and 1 little square. And let's see if we can figure out the dimensions on those squares. So we're looking for a square that's a by a, and you can see on the top this is a across, right? So the big square is a across, but is it a tall? Let's see, it looks like it's b tall and then a little more. But remember how we got this little square? We got this little square by taking the long leg and taking away the short leg's length. So yeah, this is a tall because this little square fills in the difference between the short leg and the long leg. So that square on top is A tall and A wide. So this top square is A squared. Now how about the bottom square? Well, the bottom square is B wide. You can see that at the bottom, right? And then the height is also B, because this height is cut off by the square. The square was created to cut off a length B from the length A. So the width of this bottom square is B and the height is B. So what you have here is exactly a square, A squared, and exactly a square, B squared. And it's created out of the same exact area that you use to make C squared. So this is the fat L shape that is making up a big square A squared and a smaller square B squared. This is also your class activity, so why don't you take a picture before it gets disbanded. You do need a picture of your cutout shapes. So if you haven't cut out the shapes yet, you'll need to do that at home, or there's some scissors floating around and you might be able to get it there. But the class activities are for you to be participating and working along, and so you cut out the cards and show that you're helping to work along with the rest of the class. So once you have your picture uploaded, then we'll talk about, well, how do you show this proof? How do you show this proof? So let's get it uploaded, and then we'll sketch this picture. I think I can push it up a little bit and still be on screen. There. Okay, so let's draw this. Let's make 3x5 triangles like you cut out of the paper, like you cut out of your 3x5 cards to make your template. I'm not going to try to be to scale with the C squared. Instead, we'll rely on our labeling of A, B, and C to show that we are making the same triangles here, okay? So I'm going to make 3x5 rectangles and then cut them on the diagonal just like we created the actual templates. So just copying the shape that we made, that fat L shape. So you can make the 3x5 rectangles and then cut them on the diagonal, and you will have your right triangles. So once you've drawn the figures, the squares and the triangles, they do need to be labeled because we're not trying to be to scale. In fact, anytime you're looking at mathematical drawings, the mathematicians do not assume they are the same size unless there's labels indicating that. So the C's show that we're matching the length C over here in intent. And the A's mean we're matching the side length A. So mathematicians label to indicate what matches. Okay, so we have the long legs are A, short legs are B. These are right triangles. We put little right corners on. And last of all, there's our little bitty A minus B square. A minus B by A minus B. So this proof has the least amount of algebra, but you do need to indicate you knew what you did. So once you have the squares and the triangles drawn, you need to indicate to your reader where the A squared and B squared are anyway. So draw with a different color, draw a little dotted line here and indicate this is a square a squared, and this is a square b squared. And then at the bottom, we'll just finish our discussion and say c squared equals a squared plus b squared. So this has no algebra whatsoever except for the Pythagorean theorem, but it relies on you labeling your drawings correctly and indicating where is the a squared, where is the b squared. I mean, you can see a square c by c, but you have to point out the a by a. That's a little difficult to see, so you have to make sure you point that out. So I know you know where it's at. Anybody have any questions? We have three proofs. Hopefully one of them clicks with you. As I said earlier, I have different ones get handed in. I've never had just a preponderance of one or the other, and so I continue to show all three since it seems like different ones click with different students. Well, we're moving on to 4.2, so let's take a look at 4.2. Four point two is called the art gallery theorem. How many of you have gone to an art gallery? Yep, me too. How many think you need security guards there? Yeah, I guess that's a big problem in Europe. Many of the wealthiest states exist by letting tours go through, but that means that all those expensive, valuable things people are looking at need to be guarded. So here is a floor plan for an art gallery. If you stand in the corner marked A, which walls or parts of walls can you see? What if you stood in the corner marked B? How many guards would you need, each standing at a corner, so that each wall could be seen by at least one of the guards? The guards can turn their heads, but they cannot leave their corners. So they can't leave their corners because we're thinking about this in the terms of security cameras also, a security camera that had a 360-degree view. So I'll go ahead and we'll transfer this drawing to a piece of paper here so we can all be marking it up, okay? So let's draw this art gallery. So this is an oddly shaped art gallery. I'm going to an art gallery this weekend, actually, the Payne Art Center in Oshkosh. Has anybody ever been to the Payne Art Center? Yeah? Go ahead. They're doing Rooms of Blooms this weekend, so I'm going to go there with my daughter and some of her in-laws. Did you like it? I don't think I've been there. Okay, good. Well, let's see here.
I like the Art Institute of Chicago better, but
The Art Institute of Chicago is better, huh? But it's a little further. You know, and I wouldn't even mind the drive if it wasn't for that traffic. I just can't take that traffic.
Tolls get expensive.
Tolls do get expensive, yeah.
Ugh, I don't like driving there anymore, that's why.
So A and B are supposed to be on the inside of the building, not the outside of the building. Now let's think about what the guard at A and the guard at B can see. So can the guard, well, who can see up here in this corner? Can A or B? No. The walls are in the way, aren't they? How about in this tip? Can anybody see up here? Who can see up here? B. And how about up here? Who can see up here? Just A. Yeah, so basically they can see in a straight line until their vision hits a wall. So B can see everywhere in this big rectangle down here. But can't see into any of those little points except this one. So we're going to be looking at the art gallery theorem, which discusses how many security guards are necessary. This is a branch of computational geometry, an area of mathematics dealing with efficient methods of computing things involving geometric objects. So computational geometry has a lot of overlap with the computer science area. Well, let's look at some floor plans that are possible in a museum. Okay, so you could have a floor plan that was kind of a C shape with some open doors here. Anybody ever travel to Mexico and the hotels don't have doors? Like there's these big pillars in these resorts, and yeah, they're so beautiful, and you think, well, anything could come in here, but they don't. It stays really nice. In Wisconsin, we'd be flooded with mosquitoes. Okay, or you could have a art gallery with a big courtyard in the middle. Or you could kind of have a modern view of an art gallery that's more like a starburst. Or you could have a more traditional art gallery, which is a rectangle and then has walls extending out for exhibits to hang on. Well, we were discussing these art galleries in the in the first class that I have, and the computer cut out, so that's where we ended. And I keep all my classes running the same so that I don't get goofed up over where we're at. So that's where we're going to end too. So have a wonderful weekend. I'll see you on Monday.
Yay! I was too enthusiastic. See. What were you saying?
I was saying my dad's been there.
I've been there 3 times.